So we're factoring quadratics here, and when I say factoring quadratics, I know it's a quadratic because the x is to the power of 2. So anytime you see that we're starting with x squared, it's a quadratic. And the factoring here, it does require the special factoring a quadratic method. We cannot here start by just factoring out a greatest common factor because there is no greatest common factor other than just 1. There's nothing I can divide out of all 3 terms. That's what tells me that I have to use the method where I say what 2 numbers add to the middle number and multiply to the last number. So what we're doing is we're looking to see what 2 numbers add to 3 and multiply to negative 10. Well, what did we find for those 2 numbers? Yeah, negative 2 and positive 5. Now, negative 2 and positive 5, those are just 2 numbers, right? How does that help us? Well, whenever we factor a quadratic like this, we end up with 2 sets of parentheses, and those 2 numbers are the 2 numbers that go into the parentheses. So the plus 5 is because the 5 was positive, and of course the 2 is negative, hence the subtracting 2 there. And it's always going to be starting with x, at least when we're factoring the quadratics like we've seen so far. Later this year we'll see how we can use the same kind of technique to factor even higher order polynomials, like we'll be looking at factoring a quartic this way. That's where it starts with x to the 4th. And there'll be some other tricks like that where you can use all the same techniques that you have, which is why we start with this. We want to make sure those techniques are built up. Now, before we go into the other one, do you see why this is the answer for this? All right, so why does it work? Because if I multiply this back out, I'm going to end up with this. To prove it, I'm going to do that really quick here, because I'm going to do x times x, x squared, x times 5 plus 5x. Then I do the minus 2 times x because I'm multiplying everything in the first parentheses times everything in the second parentheses. And you notice that when I go and simplify this, I add those middle 2 terms to get the 3x, and I multiply my 2 numbers in order to get the negative 10. Hence why we're looking to see what adds to the middle and multiplies to the last number. All right, we repeat the process with the second one. But with the second one, you may well have been looking at it and thinking, what are we adding to? Because we're not adding to x. It's always the number that's in front of x. Well, what number is in front of the x here, even though it's not written in? Yeah, it's the negative 1. Some of you might have been thinking 0. It's not 0, because if it was 0x, it would just be gone. It wouldn't even be there anymore. So it's got to still be a 1. And of course, the minus in front of it makes it negative 1. So in this case, we're looking to see what 2 numbers add to negative 1 and multiply to negative 20. And I know that once I find those 2 numbers, I'm just going to be plugging them into the parentheses that each start with x. All right, so I start thinking about what 2 numbers multiply to negative 20. I always start with the multiplication part first. If you find yourself having trouble with these, a lot of times just making that little switch is going to help a lot. Instead of worrying about what adds to, focus first on what multiplies to the negative 20, because there's a lot fewer ways to get it. So you limit the number of options that you have to cycle through. In this case, 5 and 4 are only 1 apart. And hence, if one's positive, one's negative, we're going to be getting a 1 in the middle. So I know it's going to be a 5 and a 4. And I know one has to be positive, one has to be negative, because I'm multiplying to a negative. How do I know which one is going to be which? Well, notice I'm adding to a negative here. If I'm going to add to a negative, that means I have to have more negatives than I have positives. Therefore, the 5 must be the negative, and the 4 must be the positive, and we're done. Please write this equation above your first graphing grid there. This is y equals the absolute value of x. Absolute value is those 2 vertical bars. Yes, those 2 vertical bars on either side of the x there. And absolute value, is, you may recall, means that whatever the inside equals, I make it positive. Technically speaking, it's the distance from 0, But effectively, that just means make whatever is inside positive. All right, so if I was going to be graphing this, which is exactly what we are going to be doing, do you remember then what shape of graph this is going to be? It is going to be a V-shaped graph. Now, why is that? Well, let's go way back. Imagine if you were making a table. I know I'm not going to take tons of time on making this table. If we were making a table for this, we might go 0, 1, 2, and the absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. Because if it's already positive, it just stays positive. And so that's why on the right-hand side, you see it starts at 0, and then it just keeps going up 1 over 1 all the way along. Because like the absolute value of 5 would be 5. Hence, we get to 5, 5. But on the left-hand side, what if I grab x being negative 1? What's the absolute value of negative 1? 1. And the absolute value of negative 2, of course, is 2, and so on and so forth. And so we end up on the left side, again doing up 1 over 1. Just in this case, we're going up 1 as we go left 1. Because, for instance, the absolute value of negative 5 is a positive 5 there. This is why it's a V. Because basically, it's a line. It's the same graph as just plain old y equals x over here on the right side. And y equals x is a line. But on the left side, it's the same thing, except we're making them all positive. So still the same shape, still that line. So basically what you see here with this graph is it's a line that bounces. It's a line that goes down until it hits 0, and then it bounces back up again, because of course it's not going to be negative. Now make sure that you have this written down, copied correctly, because this is our absolute value parent function. And today's going to be all about these parent functions. Because as we were doing our work last week, that was one of the things that I was saying, is that at least with a few particular graphs, we're a little rusty on exactly what the graph looked like, what the starting graph was. And if we can get these down, then the rest is going to be cake. So this is a way to make sure that we fill in any of those gaps that are so fundamental as we go forward. For the second graph, please write this equation above your second graphing grid. And as we talked about earlier when we were doing the factoring practice, this is called a quadratic. It's quadratic because the x is squared. So here we're graphing the quadratic parent function. Well, again, we could think about what if we actually wanted to make a table of values and get this sort of a thing. Well, I might try starting with 0. 0 squared is 0, so that would tell me I have a point here at 0, 0. 1 squared is 1. Okay, 1, 1. And then 2 squared is 4. And so now this is a very important moment here. If you understand why that is and how it gets plotted, then a lot of the graphs that we make start becoming a lot easier, because we're seeing that basically what I'm doing is I'm taking whatever my x is, however far I go over, and I'm just plugging that into the parent function. And so I'm squaring it to get 4, which means I go over 2 and up 4. And notice that if I'm saying it in terms of over 2 up 4, where am I counting from? The first point or the last point? Over 2 and up 4 is from the first point. Yeah, it's from 0 here. And so we're going to be moving these graphs around a lot this year. As we do so, knowing what this parent function looks like means you're going to know what all the other graphs look like as well. All right, what if I did 3 squared? 3 squared, of course, is 9, right? And so I go over 3 and up 9, again, from that very first point. Well, this is part of a graph. I can see what's happening over here, and I'm sure that you know what this graph looks like because you're remembering it back from like Algebra 1 and all that. But do you remember and understand why it's doing what it's doing on the left? If not, let's take a quick look and see, because it's kind of like the absolute value. Because if I take negative 1 and square it, I'm doing a negative times a negative, and a negative times a negative is a positive. And so negative 1 squared is a positive 1. Just like negative 2 squared is a positive 4. So you notice then, this one is also bouncing. Just it's not a line that's bouncing, it's the curve that is bouncing. And so it's again symmetrical across the y-axis. It's symmetrical around that first point that we plotted. It's, lazily we'll call this a U-shaped graph. But do you remember what the technical term was? Yep, this is a parabola. May also be worth noting there, if you did not remember that, to write down that this is a parabola, and our parabola came from graphing our quadratic. So if you're a little rusty on any of these terms, good to take note of them, because that way as we go forward, when I start talking about a parabola, you don't wonder what the heck I'm talking about. You already know. Next graph, y equals the square root of x. Go ahead and write this above your third graphing grid. And as you do so, you might notice that the left side of my equation here has been changing. The first graph was y equals. The second graph was f of x equals. This one is y equals. What does it change when I say y equals instead of f of x equals? Nothing. Not a dang thing. They both mean the same thing when it comes to graphing. All they are is just different notations. They're still just different ways of getting at the exact same information. So that doesn't affect our graphs. Just function notation is going to be used a little bit more as we start looking at actual values and some algebra involved and things like that. All right, so for this one, we're doing the square root of x. Now this is one that gave us a little bit of trouble as we saw it on the assignment last week, which is one of the reasons why I particularly want to pull this one out and why we're doing a lot of what we are doing here today with our parent functions, because by understanding those other ones, it's going to make this one much more understandable too. All right, again, we might have started by making a table. Well, what's the square root of 0? 0. Because 0 squared is 0. So yes, okay, we get 0, 0. So I can go ahead and plot that point, 0, 0. What about 1? What's the square root of 1? 1, okay. Boy, this is actually seeming really familiar. So far, everything has started with those same 2 points. It's amazing how often that happens. All right, what about 2? What's the square root of 2?
A decimal.
Yeah, this is where things get a little bit funky, because the square root of 2 is a decimal. I don't want to have to mess with that decimal. And so that's why square root often feels a little bit different, because I don't just next go to 2 automatically. What about 3? Do I know what the square root of 3 is? No. Nope. What about 4? Do I know what the square root of 4 is? Yes, it is 2. And so you'll notice that it's telling me that my x is 4 and y is 2, or in other words, from my first point, I'm going over 4 and up 2. That's why this graph ends up looking like it does. What's the next number that I can take the square root of? 9. And the square root of 9 is 3. So I go over 9 and up 3 from the starting point. Not the last point, but the starting point. And you can see why it has to be from the starting point here, because when we write this, like 9, 3 here, this is literally the coordinates. This is literally the point 9, 3. It's just that that same relative relationship counting from that first point is going to remain true even when we move it around. So we don't have to rely on the actual point. We can just know what that pattern is from the starting point. All right, now, we know what's happening over here now. What is happening on the left-hand side? Well, what is the square root of -1? Yeah, the square root of -1 actually does not exist. We cannot take the square root of a -1 and get a real number. Now, there is such a thing called imaginary numbers that deal with this, but we're going to save that again for later this year. That is something you're going to be coming across this year. Yes, you're going to be dealing with imaginary numbers, but for now, it's not real. It's imaginary. Therefore, we cannot plot it on a real grid, and so there's nothing over here at -1. There's no point to be plotted. In fact, there will be no point to be plotted for any of the negatives. So if you're wondering what's happening over here, the answer is nothing. The graph in this particular case with a square root literally starts right at that point and then goes over from there. This is going to be our last graph that we do. In some ways the simplest, and in some ways the hardest. Again, make sure that you're writing the equation above your graphing grid. And then this collection of graphs that you've just been making is going to be your reference going forward. So like as we do more problems like these and we start shifting them around and all that, if you're ever feeling stuck on what a graph looks like, you'll be able to look back at this sheet and see how did we make this graph? What does it look like? Because all we're doing is then just moving it. All right, f of x equals x. What is the shape of this graph going to be? This one is just a line. Why? Because, like again, since I was making tables for all the other ones, might as well be able to take a quick look at it just so you can see why. If x is 1, y is 1. And yes, notice I am calling it y, even though it's called f of x up here, because they are interchangeable when it comes to graphing. They mean the same things. F of x is telling me my y coordinate. All right, so like I have 1, 1 there. Similarly, I could do 0, 0. What about like 5? If x is 5, y is 5. Okay, this feels a lot like absolute value though. With absolute value, when I plugged in a negative, things changed. But here, they equal the same thing. So it equals -1. And so -1, -1. That is left and down. Or even like -5 goes to -5. Every single point here, the input is the same as the output. Hence, it is in fact a straight line. This is why absolute value looks the way it does. It's just that the absolute value, because it makes the negatives positive, it has the bounce. This is the same idea except it has no bounce. How do I know from looking at the equation that it's going to be a line instead of one of these other funky things? Well, with absolute value, you look for the bars. With a quadratic, you look for the squared. With a square root, you look for the square root. With a line comes from the total absence of any of those other functions. If there's nothing being done to the x other than just adding and multiplying numbers to it, it's going to be a line. That's what sometimes makes it the hardest, because we're like, I don't see the thing that I'm looking for. I don't see that one function type that tells me that it's going to be this. Well, in this case, it's the absence of it that tells you what it's going to be.